Hello everyone. As I promised, I'm going to prepare a video for the rest of chapter that we talked about analysis of large graphs, or in general link analysis and PageRank. In this video we are going to see the rest of this chapter to finish it, and as I mentioned, I just removed the last chapter that we had for stream data mining, and I made it optional for you in case that you are going to study by yourself, but it will not be asked any part of that during the final exam for the evaluation. So I just posted on Blackboard, but it is not mandatory to read that for the exam. So you remember last time that we talked about link analysis. We talked about the traditional way of search engines and also ranking the pages, and then we mentioned about the drawbacks of those, that many spammers can fool this way of ranking the page. And then we talked about PageRank that was proposed by Google, and we talked about the transition matrix, or the stochastic adjacency matrix that we created, and then we use this matrix and the initial rank for every page, which is 1 over the number of page. We had the iteration, the iterative model, to finally find a good estimation for the ranks for all the pages, and we name it PageRank. And we also deal with dead ends and spider traps in different networks, and we talked about the teleport that we added to the original algorithm to make sure that we have no issue for that in case that we have dead ends node or any type of spider traps. Today we want to continue that first by talking about topic specific PageRank. As you know, in the networks of, for example, different web pages, for every page we can consider one or more a specific topic for those pages. For example, we can say some pages are mostly related to health, or some pages are mostly related to sports, and for instance some pages are related, for example, to education, or for example politics, and even in more specific topics. So we want to know how we can integrate and consider the topics of the pages into PageRank to have a better estimation and final rank for different pages. However, based on the queries that we receive to send the related pages, we need to have some more information about that. For example, if a query has Trojan, we need to know, for example, this is actually related to the team Trojan that is related to sport, or it's related to history, or for example it's related to, for example, different computer security topics and other things that have this specific word in them. So we need to have some type of search query to be answered based on the interest that users show by providing different queries. So how we can consider and integrate a topic into the PageRank is that remember that we had random walker. When we want to consider rank for different pages, we consider a random walker, and then by having the specific topic, we can consider some small probabilities of teleporting. And we remember that we had teleporting policy last time. So the standard way is that we just use a standard PageRank, and we say that any page with equal probability. And also we had some teleporting for avoiding any type of dead end or a spider trap. Now we can say that for topic specific page rank, we can consider the topic by having some type of teleporting in extra than the one that we had for dead end and a spider trap. So the main idea is that we make the random walker a little bit biased. Means that based on the topic that we are looking for on the query, we can consider the directory or different categories of pages, and we can consider some bias when we have random walker to consider the page rank for different pages. So if you consider that capital M is the stochastic adjacency matrix that we have, and Mij means that the element in row I and column J, then we say that we are going to create a new matrix as the transition matrix, and this new matrix is has two different conditions. If the row that we are doing the adjustment on the adjacency matrix belongs to the topic, then we multiply the original value of that element by beta, like the one that we had in teleporting, and then we add up this fraction into it. Means 1 minus beta divided by the number of topic specific that we are looking for. Otherwise, if the row does not belong to that specific topic, we just multiply the adjacency matrix by beta. And at the end of the day, by having this formula, we guarantee that the matrix that we generated is stochastic, right? And also we say that all pages in teleporting, the weight of them are equal in the set of S. For example, if S is the number of S is 5, then we consider 1 over 5 weight for every of them. Of course, we can have different weights for different pages by having more specific information about the topics that we are looking for, but the main and the simpler approach is to consider equal weight for all the topics for teleporting. So how we can do that, and then at the end, when we create the stochastic matrix A, instead of considering matrix A, we just consider matrix instead of considering matrix the original matrix M, we consider matrix M to finally find the ranks for all the pages. Let's see some examples. For instance, this is the graph that we have. We have 3 nodes or 3 pages, Y, A, and M. And then based on this graph, you already know that how we can create the weight of different links. For instance, from Y, we have 2 links, one to itself and one to A. Therefore, the rank of this would be 1 over 2, and the rank of this is 1 over 2. And from A, we have 2 links again, from A to Y and A to M. Therefore, the weight of that is 1 over 2, and the weight of this is 1 over 2. And from node M, we have only 1 link to itself. Therefore, the node would be 1. So in this case, if we want to create the adjacency matrix, this is the adjacency matrix that we have. This is the original matrix M, right? And then, because in this specific problem, we say that we have some topic specific in here, Y and A are those topic specific that we want to have some bias. Means that we want to have the final transition matrix by considering these specific 2 topics. Therefore, we want to have to give more weight to them. And we consider the beta, or the parameter, is 0.8. Now, because the topics that we are interested are Y and A, therefore we say that, as you see in here we say beta, multiply by the original matrix, right? Therefore we say beta, this is beta, multiply by original matrix, plus 1 minus beta, multiply a matrix that have only values on those rows that are related to the topic specific. If you see, this is y, this is a, this is n, therefore this row is y, this row is a, and this row is n. Because y and a are topic specifics, therefore in this matrix we have 1 over 2 for y and 1 over 2 for a. And remember again, each column, the addition of each column should be 1. Now to create the matrix A, we compute beta times the adjacency matrix plus 1 minus beta multiplied by this matrix. This matrix is actually 1 over S. This is the matrix, and this is 1 minus beta. Right? So this is beta, this is n, and this is 1 minus beta and 1 over S, which is this matrix. And if we compute this, then we have the final matrix A. Let me clear this and see how we can compute that. So just see that in here, for example, we say 0.8 multiplied by 1 over 2, which is 0.4, plus 0.2 times 1 over 2, which is 0.1, and the summation would be 0.5, which is 5 over 10. Or for example, for this value, we say 0.8 times 1 over 2 is 0.4, and then 0.2 times 0 is 0, therefore it is 0.4, or 4 over 10. Now this is the matrix that we are going to use to compute R equal to A dot R. For example, what is the original value of R? The original value of R, because we have 3 nodes, is 1 over 3, 1 over 3, and 1 over 3. And we have the matrix that we have 5 over 10, 5 over 10, this matrix, and 1 over 10, and then 5 over 10, 1 over 10, 1 over 10, 0, 4 over 10, and 8 over 10. Now we can multiply that to have, for example, if this is R0, R1 becomes this value. Therefore 5 over 10 times 1 over 3 plus 5 over 10 times 1 over 3 plus 1 over 10 times 1 over 3 would be the new value for this element, and so on. And we can continue until we reach to a stable R, and then we consider this R as the rank of all the pages Y, A, and N. Let's see another example. In here we have 4 nodes, right? And based on the links that we have, this is the original weights of different links, right? Because from 1 we have 2 links to 2 and to 3, therefore each weight would be 0.5 and 0.5. And from node 2 we have only one link to 1, therefore the weight of that is 1. And from node 3 we have only one link to 4, therefore weight is 1. And then from 4 we have only one link to 3, therefore the weight would be 1, right? Now we say that this is the regular one. So the matrix, the original adjacency matrix is, if we say node 1, 2, 3, and 4, therefore we have from 1 to 2, and from 1 to 3, and then 0. From node 2 we have only to node 1, and from node 3 we have only to node 4, and from node 4 we only have to node 3. So this is the original adjacency matrix. Now we want to, by considering this topic specific, so this means that we want to have some bias only for node 1, and the parameter is 0.8. Therefore, we want to say, okay, we want to consider 0.8 multiplied by this original matrix plus 0.2 times the matrix 1 over the number of S, right? So the number of S is only 1, right? And only node 1 is the topic that we are interested. Therefore, we have 1, 1, 1, 1, and then the rest of them would be 0, right? So the final matrix would be matrix A. We want to know what would be matrix A, right? Let's see how we can compute. I just give you one example. For instance, for this element, we say 0.8 times 0 plus 0.2 times 1. So this becomes 0.2. Or for another one, 0.8 times 0.5, which is 0.4 plus 0. So therefore this one becomes 0.4. 0.8 again times 0.5, which is 0.4 plus 0.2 times 0, which is again 0.4, and then 0.8 times 0 plus 0.2 times 0 would be 0, right? So right now this is the original one for column 1. Now this is the new one, right? So this means that after applying this multiplication, see here, in here we have 0.2. This is 0.2 from 1 to itself, and then from 1 to 2, 0.4, and from 1 to 3, again 0.4, right? And then we can continue. For example, I just go for the last one to see what would be that. So for the last one, 0.8 times 0 plus 0.2 times 1, which is 0.2. And then we have 0 in here, and also we have 0.8 times 1, which is 0.8, and finally we have 0. So in here you see node 4, we have 1, 0.2, right? And then from the original one, from 4 to 3, 0.8, right? So the new one would be these weights that we have in here. Okay? And then, for example, this is original vector r, right? And then by multiplying a times r, we get a new r, which is this one. Or again, we continue, and then, for example, at the end we reach to this vector r as the ranks of all these 4 pages by considering node r as the topic specific that we have, right? Let me remove these, and then if you see the next, so in case that for example, if we consider only topic 1 and beta equal to 0.9, then for r would be this one. if we consider again 1 and then beta equal to 0.8, which is actually this one, or we can consider beta equal to 0.7, and you see when we change the value of beta, the final value of ranks would be different. Or for example, if all of them are interested, then we have the vector R like this. Okay? So the only thing that we need is to create another matrix by considering the parameter beta, and then use the new matrix to create a stable set of ranks for all the pages. And how we can consider the topics? By having different policies. For example, we can give a menu of different topics to user, and user can select the topics that they are interested. Or we can classify queries into different topics, right? Or we can consider the context of the query, right? For example, if the query is launched from a web page that is, for example, talk about basketball, we can consider, for instance, sport, right? Or based on the history of the queries, right? The queries of the previous histories we can consider and select the topic based on the history of the queries. And different strategies, user context like bookmarks and other policies that we can consider the topics of that. And the next topic that we want to talk in here is combating the web spam. And as you know that, and also we last time talked about spamming. Spamming is any type of action that some people can do to create a fault and wrong position for their web pages that are not actually related to a specific page, or do not have any specific relation or value to some pages. And any web pages that are result from these policies and these actions are considering a spam. And as you know, the statistic says that approximately 10 to 15% of all the web pages are actually a spam. And remember last time we talked about web search history, and the early search engines were just crawl the web to find some pages that have those specific words that are inside the query, and then bring those pages into the user. And also the very first algorithms for page ranking, they just were looking for matching some words and some queries inside the pages, right? They consider the number of times that those query words appeared in the page, and also they give some weight, for example, if that word is inside the title or inside the subsection or different chapters. And remember that we had, based on this very naive way of page ranking, many hackers were able to exploit this type of search engine to fool these type of search engines to send and direct the users to their own spam pages. And remember, for example, we had for the web page that, for example, is a shirt seller, and they want to bring all the attentions of the sports to their own pages, right? And we said that, for example, they can put 1,000 times of that specific word inside their page, or they run the query and find the pages and put the content of those pages in their own page, right? And all of these techniques that spammers will do are considered term spam. So term spam is a set of techniques that those people, those spammers do to fool their users to send the directions to their own pages. And based on that, we had some solutions by Google to get rid of those type of spammers. And one of them is that instead of believing what people say about themselves, we consider what other people say about those people. Means that if I want to be a good person, it is not enough that I say I am good. It is important that other people say, yes, he is a good person, right? And therefore we consider the anchor text and whatever we have around them to see that one referred page is a good page or a spam page. And based on that, we consider some type of PageRank algorithm that we had in the previous lecture about Google PageRank. Now we want to see if we have some spam farming, how we can get rid of them. So again, Google consider spam farms that are usually developed by spammers. And if you want to see the spam farms, they do first some categorization on different pages. They say that all the web pages can be categorized into 3 different categories. The first category is those pages that are not accessible to the spammers. Means that they are not able to modify those pages. For example, a page of uWindsor, homepage, the website of uWindsor, or for example, page of CNN or other popular web pages. The spammers are not able to access those pages to change them. Another category is the good pages, but they are accessible. When we say accessible, means that spammers are able to modify the content of them. For example, different pages that are blogs and give the permission to the users to put comments. And then spammers can put the comments and the content is actually linked to those spam pages, right? So accessible pages do not belong to the spammers, but spammers have access to modify them. And finally, the owned page of the spammers, the pages or the web pages that spammers will create by themselves. So this means that they control those pages completely. Now, based on this categorization, they want to do this type of action. For instance, these pages are those pages that are under complete control of spammers. And these pages are not accessible in any way, for example, CNN or say uWindsor or for example CBC or other popular pages. But there are some pages that are somehow accessible, for example blogs, right? Spammers can put their comments inside that, and inside the comments they can direct users to their own pages. So in this way, spammers can create one web page and then put different comments inside the accessible pages, somehow modify them to have some links to this specific spam, and also they have the ability to create many spam pages that they have incoming, outgoing and incoming pages from links from that specific page. Now for this specific page, the page rank might be high because it has many incoming and many outgoing links that create a high rank for these spam pages. Now we want to see how we can get rid of that. The approach by Google is actually creating trust rank. Instead of page rank, we want to convert page rank to trust rank. And how we can do that? By considering a specific concept named spam mass. We want to have some parameter, some value to say that, for example, if the spam mass of a page is high, then this means that that page is most likely a spam. If the spam mass of a page is low, then it is most likely not a spam. We want to have some formalization for computing the spam mass of every page, and then we consider trust rank. So to combat the spam links, we want to have these two ways. For the trust rank, we can have a simple solution. Remember that we had teleporting, right? We had the concept of teleporting, for instance, to get rid of dead ends or a spider trap, or by aggregating the topic specific. Now we can integrate teleport to convert page rank to trust rank. How? We can have some teleporting, not for example to a specific topic, or not in case of a spider trap or dead ends, but teleporting to some trusted pages. Means that when we have all the web pages, we select some of them that are very trusted. For example, we say page of University of Windsor, or page of University of Toronto, or page of, say, Government of Ontario. These are trusted pages. And then we consider these as the teleport set. And whenever we want to do teleporting, we do teleporting to these pages. So therefore, we propagate trust through those trusted pages. Right? It is a very simple solution by considering teleporting to trusted pages. However, we have two conflicting considerations. First of all, if we want to inspect all the pages and then we consider some of them as trusted pages, we need to have this set as small as possible. We don't want to have a huge number of pages as those type of trusted pages, right? And also we want to ensure that every good page gets adequate trust rank. Means that if we have a good page, we should make sure that this page has a high and adequate trust rank, right? So therefore we have a good teleporting to those specific pages, and we make them reachable, right? So suppose we want to pick a seed set. When I say seed set, the set of those trusted pages. How we want to do that? We can have two different policies. One policy is that we compute page rank, like the way that we learned last time. And then when we have rank for every page, then for example, we consider a parameter k, and then we put those pages that have rank, and that high rank, and we just consider k top ones, and we put them inside the trusted pages, right? For example, if we say k is 1000, we select the top 1000 pages and we put them as the trusted pages, and we do the teleporting to only those 1000 pages. And another strategy is to consider some trusted domains. Means that, for example, every web page that has the domain of education, or every page that has a domain of government, we say these are the trusted pages. This means that trusted pages come from trusted domains. These are two simple and straightforward strategy to consider the seed set of trusted set or trusted pages to do the teleporting to those specific pages. And the next thing is to have a specific parameter. We name it a spam mass, right? The weight of each page based on being a spam or not. Means that the higher the mass, the higher the probability of that page being a spam. How we can formalize that? First of all, we compute the page rank of every page. and we name it R of P, right? For example, we have a node A, and then we realize that the rank of this one is, for example, 0.9, right? So this is R of P. And then by considering the trusted pages, we revise this page rank by teleporting into trusted pages only. And then therefore we have another value for that. For example, it becomes 0.8, right? So this is the regular page rank, but this is the page rank based on applying teleporting to only the trusted pages. Now we compute the fraction of the differences between RP and RP plus divided by RP, and we name it span mass of page P. And then we say pages with high value of this fraction, they are most likely spam. Means that if the rank of the page is very close to the rank of the page to the trusted pages only, then the spam mass is very small. But if the rank is high, but the rank to the trusted page is very low, therefore the difference is very high, and then therefore the spam mass is high, and then it is most likely spam. Okay, so this is the final things that we want to talk about this chapter. As a summary, in this chapter we first talk about the traditional way of PageRank, and then we talked about the algorithm for PageRank proposed by Google, and then we talk about the two specific cases, dead ends and spider traps, and we said that we can get rid of these. But for dead ends we have two strategies. We had this before, first by removing the dead ends recursively and compute the ranks, and then again reconstruct the dead ends and find the ranks, or by teleporting. And also for the spider traps, we saw that by teleporting we can get rid of this type of spider traps. And then we talked about, in this session, we talked about trust rank, which is a specific version of PageRank by considering some pages and also some topic specific. And also we talk about spam mass and finding a parameter to say that one page is a spam or not. By having this, we end this chapter and also end of all the course content of this course this semester. Later on, you already received an announcement for changing the evaluation, and also about the type of the final exam, which is a hybrid one, online and take-home exam. By take-home exam means that I give you a question on Blackboard, some question on Blackboard, and you have some time to answer and submit them electronically on Blackboard as well. So if you have any question, you can ask me by email, and also I try to have the same content during the live session on Wednesday in the coming week. And later on I will post this video for you as a reference after